Hi! For this video, we will be going back to our previous lessons on chemical bonding, particularly showing some significant structures that will guide us to analyze how each of the atom, when they make a compound, will form the different shapes and structures that they're representing. But remember, in this video, it's going to be more on lecture type, and I hope that you're ready to just listen to this and look at the graphics and help yourself. Please force yourself to recall the basic of chemical bonding that were previously taught to you. Let's start with recalling the LEDs or the Lewis electron dot structure of methane. That's your CH4. Now remember, the LEDs is the one in which you will put dots and then connect the central atom to the terminal or surrounding atoms. CH4, that means you have one carbon surrounded by four hydrogens. And you know that carbon has four valence electrons as represented by its outer electron configuration of the last energy level. So it's 2s2, 2p2. The complete is 1s2, 2s2, 2p2. However, in chemical bonding, you know that it's the valence electrons that participate in the chemical bonding process. So we highlight only the last energy level electrons. And because this is about molecules, so the electrons of each element are shared, because this is the Lewis electron dot structure of our covalent compounds, in which organic compounds belong to it. So carbon is 2s2, 2p2, and of course, if there are four hydrogens, each hydrogen will have a very simple electron configuration of 1s1, representing its single electron to be shared. Now, let's look into the details. We know that when we draw the Lewis electron dot structure again, carbon having four valence electrons will share each of these electron to every electron of every hydrogen. And so there are four hydrogens that will also share with the four electrons. That means you won't see any lone pairs in the carbon side. You know that we've been studying carbon in organic chemistry, so carbon has four valence electrons, and that should share everything so that carbon will have 2, 4, 6, 8, and it follows the octet rule for them to be stable. Now, behind this Lewis electron dot structure, there's something going on with its electrons in terms of its orbitals. And when we say orbitals, we talked about the s, p, d, and f. We did this lesson when we had electron configuration. So SPDF, S has one orbital, P has three orbitals, D has five, and then F has seven. For now, because we're focusing on a very simple element, carbon, for organic compounds, that means we'll focus only on the S and P. Now, if we draw the orbital diagram of carbon, so S2 will look like this with two arrows, P2 will look like this, Px, Py. Remember, P has three orbitals, and that represents the three orientation of P. The three orientation of P is Px, Py, and Pz. So Px, Py, and Pz. Remember that the shape is like a dumbbell. So it has two lobes on top and below. So that will be your Px, Py, and then Pz. So that looks like that. S is just a spherical shape. You know that. While S, 1s1 for hydrogen, is very simple. It's just an S1. So you just draw one arrow representing your one electron of your S orbital. So how will they interact? That's the focus here. How will they interact when carbon and hydrogen bond together to form your CH4 molecule? Is there really room for each hydrogen to share? Is it with carbon? So let's see. So what's gonna happen is carbon needs to be stable to follow the octet rule. How will it be stable? All the p's have to be filled or have filled, right? Now, because S2 is complete, but it belongs to the second energy level, what happens is the one electron of S will jump to PZ and will have all the S and 3p orbitals half filled. So when it's half filled, that means carbon will readily bond or share 4 times. Again, this will readily bond 4 times. That's why carbon is can possibly share 4 times. And the 4 times can be all single bonds, right? It can also be, let me just represent that, it can be all single bonds. It can be single, single, and then double. It can be double, double, or triple, single. That is the reason why carbon can have 4 types of bonds. On the other hand, hydrogen doesn't change. It has half-filled s orbital because it's s1. And if you look closely, this and this, it perfectly fits. Carbon has 4 half-filled orbitals, and since there are 4 hydrogen with half-filled orbitals, they can share per orbital to completely fill up each other. In other words, hydrogen and carbon complete each other. That's what happens during the chemical bonding process. So go back to how the electron of S from carbon jump to P so as to facilitate the bonding process. So this is the mechanism of carbon's bonding. So it facilitates the chemical bonding process by it's a natural movement of the electron from S, it goes to Pz so that all S and P in the second energy level becomes half filled, ready to bond to the surrounding atoms, whatever that is. Okay, I hope that's clear. If it's not clear, go back to what I just said and draw the orbital diagrams on your notebook. So, what's gonna happen now is how will it look like? So, how will it look like? Now, let's analyze. For carbon, it has an S and it has 3p orbitals. And I just draw a while ago how p looks like. It looks like a dumbbell. So, this is your px, this is your py, that's your pz. And the S is spherical, so that's how an S looks like. And for 1s1, because it's just an S, it's all spherical. So, how will we combine this and this? How will they look like? So they're going to look like this. There will be what we call the fusion of these orbitals because they're bonding. So there will be a combination of your S from the H, which are represented by these four spherical circles here, and they will share and fuse with the existing 3p orbitals of carbon and the 1s of carbon. I mean the s orbital of carbon. Remember, size matters. S is smaller in radius than the p, and the 2s of carbon should be bigger than the 1s of hydrogen here. That's why size matters here. Remember that each p orbital is on x, y, or z axis at 90 degrees angle from each other. That's how they arrange to avoid repulsion. And also remember that, of course, s orbital is smaller in radius than p orbitals. So when we combine all of this, how will they look like in real sense when they really completely bond each other and form the molecule? How will they look like? Now, there is an evidence that says in the actual molecule itself that the CH bond in methane has the same length. So all the CH bond in 4 areas, in the 4 bonding regions, have the same length. It's 109 picometer. And each HCH bond angle is also the same. It's 109.5 degrees, which is the angle of a tetrahedral. CH4 is a tetrahedral because it has 4 surrounding atoms with 0 lone pairs. So it's tetrahedral. And it perfectly has the same angle from HCH bond. But how is this possible if S and P orbitals are different sizes from one another? And the S and P orbitals are at 90 degrees, not at 195.9 degrees angle. The answer is because of hybridization. Now, I will stop in this slide and watch out for the next series of this video. So I will be describing the details about carbon hybridization. So we will start with this in the next series. So I hope that you've learned something from this. Bye for now, and God bless you.